Hey everyone, we do RDMA at the cloud scale here at Oracle. You may know that we've sponsored the Red Bull racing team for years now. Our name is on the side of the car. They use the RDMA networks that we built to do computational fluid dynamic simulations. They can simulate the airflow that goes over the cars. Other automotive customers also use our RDMA networks for HPC. And these clusters can be huge, up to 1,000 nodes running these computational fluid dynamic jobs, which is really cool. But nowadays, it's hundreds of megawatts of compute. So nothing's as cool as building a 100 megawatt AI megafactory. This is our Stargate complex in Abilene, Texas, where we're building giant amounts of AI compute for OpenAI. Well, today we're going to tell you the story of going from 1,000 nodes to 100,000 nodes of an RDMA network. My name's David Becker. I'm architect for GPU clusters at OCI, and I'm here today with Jag.
Hi, I'm Jag, and I'm a distinguished engineer with OCI. And while David said 100,000 node cluster or 100 megawatt cluster is cool, it's also very hot, and cooling it is a challenge in itself. So let's take a look at how we got where we are in terms of our journey as a cloud provider in RDMA. Firstly, for those of you who may not be familiar with OCI, OCI is a fully featured tier 1 cloud. It's a hyperscaler cloud, and Gartner has quantified us or classified us in their magic quadrant, which is the top tier clouds in the world. So that kind of gives you an idea of the features and the functionality available in the cloud. It's fully featured with hundreds of services. And it's also a public cloud that's global. We have 50 regions, actually over 50 regions in 26 countries. And all of these regions are interconnected using OCI's own global backbone that we run ourselves. And there are many different kinds of workloads, many different categories of cloud. We have commercial regions, commercial workloads, sovereign customers, government customers, and even multi-cloud customers. So it's a very diverse, feature-rich global cloud. Let's look at the history of the cloud. We started building OCI in 2015 as far as the design goes, and we first launched our first region in Phoenix, Arizona in 2016. And shortly after that, we started working on RDMA, which is what we're here to talk to you about today. And we launched our first RDMA offering as what we call the cluster network. That's an OCI term. That's the product customers consume in 2018. And that was targeted initially for low latency workloads like high performance compute workloads, like scientific computing workloads, as David talked about, as well as Oracle database workloads, in particular Oracle Exadata. And we'll talk about that in a little bit shortly. And these HPC workloads are scientific computing workloads, simulation workloads, and Exadata workloads are database workloads. And as you may know, RDMA stands for Remote Direct Memory Access. And basically, it's DMA, which is generally within the bounds of a computer, done at the scale of a network. So you're basically doing a data transmission from a sender host to a receiving host without involving the CPU or without involving the operating system. So it has tremendous benefit in terms of throughput and low latency. And HPC workloads require that, Oracle database workloads require that, and increasingly LLM, GPU, training, and inferencing workloads needed. And so we first launched HPC at OCI in 2017. We launched publicly in 2018. And then we launched Oracle Exadata database workloads in 2018. And it may not be apparent, Exadata is a very important, critically important workload for Oracle because virtually all the databases in the OCI cloud run on top of Exadata. And we have this joke internally, which is that Will runs on top of Exadata and Exadata runs on top of OCI cluster network, which is RDMA under the hood. So virtually all the software as a service SaaS product, platform as a service product, and many of the IaaS products use Exadata under the hood. And increasingly GPU LLM workloads also run on top of this RDMA network. Now, in order for us to build this product, we had to do something that had never been done in the cloud before. As you know, cloud is fundamentally about large scale. So you have this concept of utility computing where you have lots of resources at scale and customers get to have capacity as and when needed for however long they need it. So that requires large volumes of capacity, which is generally geographically dispersed. And that means high latency. Whereas RDMA workloads are fundamentally about low latency. So we had to do something new. And the way we did that is we carved out what we call islands of this cluster network within our cloud, where we control the diameter of the latency very tightly. So that's the first thing we did, which is we distance limited our cluster network to reduce the latency. Secondly, because cloud is fundamentally about multi-tenancy, as in there could be any number of customers, we needed to make RDMA work for a large number of customers. Traditionally, RDMA was a single workload, single customer on-premise kind of a technology. And we had to then make it work for multi-tenant networks. And what we did is we basically invented a way of doing overlay networks for RDMA. And in order for us to make the overlay networking work, it's also called network virtualization. For us to make it work, we had to do some heavy lifting. We needed to do multi-tenancy in a way where we're not penalizing the workload for throughput or latency. And in order for us to do that, we used a strong form of certificate-based authentication to drive the customer tenancy information, and then do the network virtualization in the network without involving latency or throughput penalties. So that was some important heavy lifting we did. Now, you might ask, how well does that work? This is actually a chart from a paper published at Sigmetrics in 2022. All credit to the team. It's a team from ETH in Switzerland. And basically what they did is they went to 4 different cloud providers, AWS, Azure, GCP, and OCI. And they also went to 3 on-premise supercomputers, and they tested how well does HPC MPI workloads work. And they were looking for this thing they described as noise, which is basically variation in performance. This is one of the charts from the paper. And basically it's a chart showing throughput, which is the curves on the right, and then latency, which are the curves on the left. And let's look who came at the top. Oh, interesting. There's this red curve, which is at the top for the throughput and almost at the bottom for latency, which turns out to be Oracle. So it turns out we have the highest throughput and second lowest latency. We had the lowest latency across all the cloud providers, and we had lower latency than 2 of the 3 on-premise supercomputers. There's one on-premise supercomputer that was just able to slightly have lower latency, but that's kind of in the noise. The key point is performance is really high. So we really were able to offer this product at almost no performance compromises. So a little bit on the underlying technology to make this product be possible. We used a specific kind of technology called RoCE to do RDMA. RoCE stands for RDMA on Converged Ethernet. And the reason we picked RoCE, because this is an obvious question we get asked, is one is we wanted multi-tenancy. And RoCE turned out is well fit for doing multi-tenancy. The other is we wanted support from multiple vendors of NICs and switches. That meant Ethernet to us, which is the E in RoCE. And thirdly, we wanted arbitrarily large scale, because cloud is fundamentally about scale. We also wanted arbitrarily large scale because being a cloud provider, we needed to be able to scale to any number of customers, any scale of data centers, and that meant Ethernet to us. That meant RoCE to us because it uses principles of distributed computing. And then lastly, we wanted to minimize cost so we can pass on the savings to our customers. That also meant Ethernet to us because that is a multi-vendor, multi-source technology. And now I'm going to hand it off to my colleague David to talk about our bare metal product.
Thanks, Jag. So now I'm going to tell you about the details of how we build our networks in OCI. We build them on bare metal. Sorry, not bare heavy metal. This kind of bare metal. So OCI has a long history of supplying customers in the cloud with actual hosts as opposed to virtual machines. Historically, clouds, our competitors, and Oracle sell virtual machines, which means the host is running a hypervisor and you're sharing the machine with other customers. Bare metal machines, the customer has the machine all to themselves, and they have full access to the machines. They can do things like upgrade the firmware on the GPUs or configure the actual parameters of the NICs the way they want. And this gives our customers the kind of performance that they need in order to maximize the AI training performance of these GPU nodes. On the right side of this, you can see the classical connection to the internet and everything else goes through the CPU and a virtual NIC, just like on a virtual machine. It's still a virtual NIC, and it goes out to the cloud with all the services and the tenant isolation that the cloud classically offers. The backend also has tenant isolation, but it has a different technology that doesn't scale as well. So on the left side, we have what's called the east-west RDMA network. And this network also has all the isolation features of the front side network, but it uses techniques that scale better and allow the low latency that we needed to do the high frequency trading applications or to do the computational fluid dynamics simulations. On the GPU nodes, these are a little more complex than your normal computer because they have a whole set of NICs on the backside. So the configuration of these nodes for your networking on Linux is actually quite complex. Oracle supplies an agent to help configure those nodes, but each GPU, in our H100 generations, we had 8 GPUs, and each of those would have a high performance NIC, the best NIC that we could buy for that era, so a PCI Gen 5 NIC. And those NICs all have full bandwidth to all the other NICs in the tenancy that you own, so all of your nodes. So if the network was 100,000 nodes, you could talk to all 100,000 NICs in that network, which corresponds to 100,000 GPUs because it's one NIC per GPU. So we discovered that the GPU customers that we had were not as latency sensitive as the simulation customers that we originally built our RDMA networks for. And this allowed us to do some more things with scale, sacrifice a little bit of latency, and they loved our latency, but sacrifice a little bit of latency and use all the bandwidth and achieve the kind of scale that we needed. So we were used to scales of 1,000 nodes, and now we had to do scales of 100,000 nodes. The 1,000 node scale, we used a network topology that looks like what we see here. So we have GPUs are the blue boxes on the bottom. They connect directly to tier 0 switches. And those tier 0 switches connect to each other via tier 1 switches. This kind of network topology is called a closed topology, and it has the property where the number of nodes that can attach to it, the GPU nodes at the bottom, is proportional to the square of the number of ports on the switch. Our switches that we used were 64 ports on the front, and that meant you could have up to 2,000 GPU nodes attached to this. But that wasn't nearly enough for our GPU clusters. So we invented the 3-tier technology here. So above the tier 1 switches, we added another tier of switches. And the math works out that the number of GPUs you could have in such a network is proportional to the cube of the number of ports in the front. So if you had a 64-port switch, you could get up to 100,000 nodes. And that's the kind of scales we need today. So now Jag will tell you about the key properties of our product.
Thank you, David. And now we'll talk about some key properties of the product, which our customers consume, and the key properties of the underlying network that makes the product possible. So the key properties of the product is, firstly, unlike some of our competitors, we went ahead and built a dedicated backend network. And David showed that in the previous section, how there is a dedicated backend network in addition to the front-end network. That requires more cost, more work on our part, but we did it because we didn't want to take any performance compromises, because RDMA, performance is of essence. Secondly, we wanted multi-tenancy. We talked about it before as well. It's a fundamental need. We must have multi-tenancy or the product is incomplete. Ours is a multi-tenant product. We can have any number of customers, and every customer gets a completely isolated experience, completely unique, isolated experience. Next, we also wanted to support multiple types of workloads. So we didn't want to just support ML, AI workloads, GPU workloads. We also needed to support HPC workloads. We also needed to support Oracle Exadata database workloads. And these workloads have their own unique requirements and expectations from the network. And lastly, we wanted arbitrarily large scale. And for that, we relied on flow topology that David just described to you, which allows us to scale at the exponent of the radix of the switch and at the exponent of the number of tiers in the network. Now let's look at the key properties of the network, which is the underlying technology that makes the product possible. The first is we chose not to do end-to-end PFC. PFC stands for Priority Flow Control. And PFC was the existing paradigm of doing raw key in a network. And PFC doesn't lend well to deployment of the cloud because PFC has well-known issues with blocking. And there's actually a really good paper that Microsoft published in SIGCOMM a few years ago where they described some of these pitfalls of PFC. So we wanted to avoid end-to-end PFC. And we did. And we'll look at that shortly, how we did that. Next is we use what we call certificate-based determination of tenancy, which gives us very strong assurances on tenancy information for the customer. Very important property of our product or of our network. Next is we have multiple what we call QoS classes in the network. Each of these classes of QoS can be thought of as lanes on a highway, where each lane, each class of QoS gets its own tailored service in the network. And we'll look at how is that made possible. And then next is we use congestion control for Rocky, and that congestion control runs on the NIC, on the hardware. So that gives us an offload, a performance boost. Next is we use load-aware traffic distribution, where switches don't just do oblivious forwarding of traffic, which is generally the existing paradigm. We went with the load-aware traffic distribution, which gives us another traffic boost. And lastly, we have this thing called network locality, where we make customers be aware of the topology of the network. In fact, we publish the topology of the network to the customers, allowing them to make the best use of the network. And this gives them a significant performance boost. Now, I touched on PFC shortly, and I touched on congestion control. Let's look at why does that matter? Why is it that we didn't run PFC end-to-end? So basically, the issue with PFC end-to-end is PFC relies on hop-by-hop flow control, which can lead into end-to-end blocking of the network for a variety of reasons, which are in a paper that Microsoft published. You're welcome to go take a look at that paper. It's a SIGCOMM paper. So we didn't want to have a network which is multi-tenant, large scale, and be blocking. So what we did is we did not run PFC end-to-end. Instead, we relied primarily on congestion control for avoiding congestion in the network. But we did find some corner cases, even with congestion control, where we needed PFC at the very edges of the network. So what we do is we allow hosts to send pauses to the first hop tier 0 or TOR switches, but no PFC end-to-end. So hosts can still gain that small performance boost by having a local pause to the local switch, but they cannot block the network. So we struck the balance of congestion control and priority flow control. The next is, I briefly touched on it, the fact that we have multiple classes of workloads running in the same network. So we can have HPC workloads needing the ultra low latency. There are, on the other extreme, ML, GPU workloads, training inference workloads that need the highest possible throughput. And in the middle sit various different Oracle database Exadata workloads that have a different balance of latency versus throughput. For the HPC workloads, what we do is we mark the ECN, which is the congestion signal that switches send to the NICs to do congestion control. We send that signal really early, that's the curve on the bottom left, and we immediately go to 100% marking. And so we clamp the brakes really early. And then on the other extreme is ML workloads, where we start marking much later, and then we slowly build up probability of marking. So we slowly slow down the workloads if there's congestion. And in the middle sit the database and Exadata workloads, which there are many different classes of sub-workloads, each striking a different balance of latency versus throughput. So really, this is a multi-workload network with multiple lanes of quality of service. So it's a much more rich network than what you may be aware of from other providers and other cloud providers. And at this point, I'm going to pass it on to David to explain how rocky has our rocky road been.
Thanks, Jag. Yeah, one of our biggest challenges is what we call optical link flap. And this is where, at these high speeds, we're at the cutting edge of what these optics can do. These high speeds, they're very finicky. And we've seen, and other vendors have seen, that these links will sometimes go down and come up more or less on their own. Through no fault of our own, it's just they're that finicky. And the issue when these links go down is that it takes up to 30 seconds for them to come back up and renegotiate to these speeds. So we've tried to invent a way to get these, we call it a debounce, to get these links to ignore brief outages. So in that sense, you will lose a few packets because the link is down, but it won't try to renegotiate. It'll just pick up from where it left off and pretend that that outage never happened. Now, this does technically violate the IEEE standard, but in terms of preserving the job and letting the training job continue, it's totally worth it, because you don't want a weeks-long job to die because a link went down or have to back up to a checkpoint that happened half an hour ago. On a 100,000 cluster, 100,000 node cluster, that would be a significant, expensive way to do things. Another challenge that we encounter is congestion. So here on this picture, you can see that GPU 1 and 2 are both running a job, a blue job and a green job. And for the natural random assignment of flows, the first switch that they send their data to decided to send both flows up to one of the switches that it's connected to. Ideally, it would have sent it to both switches and both flows could run at full bandwidth. But due to the way the load balancing algorithms naturally work in these switching ASICs, sometimes they'll decide to send both flows up to one. We need to solve this because that means both of those flows run at half speed, and the entire training job running on tens of thousands of GPUs is going to be waiting for these slow flows to finish. The network has enough bandwidth. It didn't use it, though, because of the way these switch ASICs work. So what we came up with in collaboration with our switch vendors was a way to have the switch control plane, the regular CPU on the switch, look at these flows and figure out where they can be sent to get full bandwidth utilization. And this significantly speeds up jobs because now the flows can run at full speed and it fully utilizes all the network that we built. All right, so Oracle invented a way to create RDMA networks that can be used in the cloud. And we did it at very low latency and high scale. So this is awesome for a range of applications from HPC to these days, everything is about GPU. And we learned that performance tuning is a never-ending problem. Every generation of technology needs to be tuned and optimized to get everything that we can out of our NICs and GPUs. In the future, we're hoping that there are hardware solutions to the challenges that I mentioned. So packet spraying is a promising technology that would handle the congestion control problems. We would need out-of-order reassembly to be able to spray packets evenly across the network links. And we're hoping that new generations of interconnects between the GPUs and the switches will give us the reliability that we really want. There's some promising startups out there, and we'll definitely use that technology if they're able to deliver. So I hope you enjoyed seeing how we do RDMA at scale at Oracle. Thank you.